This video is still continuing with Chapter 4 on forces, but we're going to look at Newton's third law of motion very quickly, and then also now apply that to your practice D problems on talking about different specific types of friction, how friction works, how to draw the free body diagrams with the application of friction, and then how to solve through problems with the different types of friction. So on this slide right here, we see that by definition from your textbook, literally taken from your whole textbook, it says if two objects interact, the magnitude of the force, so the number, exerted on object 1 by object 2 is equal and simultaneously exerted on the other one. Okay, so like the amount of force that you're applying to an object is equal and opposite to the amount of force the object is applying on you. So the outcome of it, like for instance, this hammer on nail and wood on nail, the hammer that is applying a force onto the nail is equal and opposite in magnitude, well, equal in magnitude, opposite in direction, at the point of contact. The result, Newton's first law, is that the nail goes into the wood. Okay, so the whole entire system is an application of Newton's third and first law. Obviously, that's talking about two different objects. Hopefully now, and let me kind of state this because I really didn't in your F equals MA video. F equals MA is talking about an object. Okay, it's not talking about the hammer and the nail. It would just be assessing the hammer, or it would just be assessing the nail. Whereas Newton's third law and, in this scenario, Newton's first law can assess two objects. Okay, so the force that the nail exerts on the hammer is equal and opposite to the force that the hammer exerts on the nail at the point of contact. So it's like a freeze frame, okay, when the hammer hits the head of the nail. And then the resulting idea is going to be Newton's first law. Okay, so field forces. Field forces, like F of N and F of G, is really what this is saying. Take a minute and read through this, but it kind of reiterates the idea of surface area, and the larger something is, the more surface area it has. Like, for instance, people at base jump that put the wing flaps on the side of their shoes versus, you know, you just fall like right out of the airplane, or you jump right off the building or off the bridge or whatever. You usually don't have those wing flaps, so you're not going to be up in the air as long because you don't have as much surface area to catch more of that wind to, i.e., slow you down, therefore increasing the amount of time that it will take you to reach the ground. Okay, it's also talking about, like, okay, the mass of the Earth versus the mass of the dummy that's falling out of this airplane. Both objects are accelerating towards each other at the same time. Like, that's kind of a crazy concept, right? So, like, this dummy that is falling out of this, has fallen out of this plane, is accelerating towards the Earth while the Earth is accelerating towards the dummy. How come we don't see the Earth accelerating towards the dummy? Okay, F equals MA, right? So if you're talking about a small mass, then you have, if you're talking about a small force, then you have a small acceleration, because the mass would then have to be, well, stop and think. Mass and acceleration are going to be indirectly related to each other. So a small acceleration would be a really massive object, whereas a large acceleration would be a less massive object. So obviously the dummy is less massive when it's compared to the mass of the Earth. So although both objects are accelerating towards each other, you technically do not see the effects of the Earth accelerating towards this dummy. Makes sense? I mean, it's like a crazy concept, right? The Earth is really accelerating towards me right now? Yeah, it is. Moving right along. So here's your next section, and this is where practice D is going to come into play. It's all about overcoming friction and talking about the coefficients of static friction and the coefficient of kinetic friction, which, long story short, is really just talking about the roughness versus the smoothness of a surface. Like, obviously, sandpaper is you know, more gritty than wax paper. So you're going to be able to slip and slide more on wax paper than you would be able to on sandpaper. So why do they put different surfaces down on flooring and whatnot, things like that? Okay, so that's kind of what we're going to get into here. The very first thing that I want you to understand is that friction opposes the applied force. So if you're pushing, like this jug of juice here, if you're pushing it towards the left, then the frictional force is going to go towards the right, as you see here. Okay, so the first thing, looking at this picture right here, what is the gallon of orange juice initially doing? So in physics terms, we just simply say it's at rest. Well, if it's at rest, what is your net force? Okay, so you need to think it through. F equals MA. Is the mass of this jug changing? No. So the mass of the orange juice jug is going to stay your constant. So you are assessing acceleration versus force, and they are directly related to each other. So if your acceleration is 0, because it's at rest, it's obviously not accelerating, then your F net is also going to be, don't forget your units, don't just say the word 0, guys, it's 0 what? 0 newtons is what you should have down there. So that makes your net force 0 newtons. Let me move this here. Why is the vector of f of k shorter in magnitude than the vector of f of s? So, my gosh, there's so much to talk about right here, but I think that if I just give you the basics, you should be a-okay. So, an object at rest wants to stay at rest. An object in motion wants to continue in motion, unless acted upon by an external net force. So this jug of juice is at rest, it wants to remain at rest. So its mass is equivalent to its inertia. What is inertia, once again, by definition? Inertia, by definition, is tendency to resist change. So you're going to want to stay at rest, right? So you can't just apply, here's a force, it's going to move. No, you have to calculate, figure out, experiment. How much force do I need to apply to this jug in order to make it move? That would be your Fs. Why is it called Fs? Because it's stationary. So stationary in physics terms is called static. So you have your static friction. So that's Fs. But you guys will know this as Fs max, because Fs max literally means that maximum point, that point right before it starts to move. So that's the maximum amount of static friction. Technically it's applied force, but obviously we can talk about static friction because it's opposite the direction of the applied force, that you can apply to the jug right before it's like, okay, I give in, let's move. I feel this external force, I'm going to now work towards this external force direction. Obviously friction, though, is opposite direction of motion. So then your F of K, so you're moving. Oh, well, I'm moving, I'm going to continue moving. Object in motion wants to stay in motion. Okay, so now its inertia is, for lack of a better term, lighter than what it was when it was at rest. Agreed? Because now you have it in motion and you are applying that force. So it doesn't take as much force to keep an object moving as it does to get it to start moving. So therefore your Fs values should be greater than your F of K values. Make sure you assess your answers when you're working through your problems on D, because you will need to solve for F of K and F of S for number 3. Number 3 has like an A, B, C, and D to it. So you should have an Fs value and you should have an let me correct myself, an Fs max value and an F of K value. Your Fs max values should be greater than your F of K values. Check out my chapter 4 practice problem answers that are posted on, the teacher page. You should be able to assess your answers against mine and see, yep, my Fs max is greater than my F of K. Okay, so that pretty much answers your why is the vector of F of K shorter in magnitude than F of S, because it doesn't take as much applied force to keep something moving. It takes more applied force to get something moving. So you're using Newton's first law there. So I just want to say inertia first law. Okay, lastly on this slide, what is the difference between Fs and Fs max? So I've already kind of assessed that for you. Fs is you applying a force to something that is at rest and you're trying to get it to move. And Fs max is that point right before it is about to move. That is the one that you want to draw on your free body diagrams. Okay, so Fs max is on your free body diagrams for objects that are at rest and friction is applied to them. So an object that's at rest that has friction on it is going to be Fs max, working opposite the direction of your force applied. Make sense? Okay, so just one more thing here. So what this free body diagram here is going to look like is that. Okay? So now when you go to draw the F of K1, you just need to make sure that the length of your F of K is not as long as, it is not as long as your Fs max, because it doesn't take as much force to keep an object moving as it does to get it started. Okay guys, so let's think about this statement right here. Look at this statement. It says kinetic friction. So are we talking about objects at rest or objects in motion? Kinetic friction. What does that mean? Kinetic friction is in motion, okay? So they are moving, whereas static friction is literally stationary. But in physics, we just simply say at rest. Kinetic friction is less than. So your F of K value should be smaller than your F of S values is literally what this is saying. So think about this. Do you have to apply more force or less force to get an object to move when it's initially at rest? You have to apply more force. What is the one-word answer that you can give me on why? The one-word answer. That one-word answer should be because of inertia, Miss Arter. Because of inertia. Okay, well, how do you know about inertia? Well, because in Newton's first law of motion, it states that an object in motion wants to continue in motion, or an object at rest wants to stay at rest. So with that in mind, you are, unless acted upon by an unbalanced force, so you are utilizing Newton's first law of motion in the idea that inertia, tendency to resist change. By the way, what is the other name for Newton's first law of motion? Looking back in your notes, you'll be able to see that the other name, the alternative name for Newton's first law of motion is the law of inertia. So do you have to apply more force or less force to get an object to move when it's in motion, when compared to the Fs? You have to use less force to get it to continue to move. So which law of motion are you applying to these two statements? You already answered that, right? This is Newton's first law. So, would it be true to say that F of K should be less than Fs max? So once again, now that we've discussed this, let's go back to our leading statement here. It says kinetic friction is less than static friction. Is that a true statement? Should your Fk values be less than your Fs max values? Yes. And once again, it's because of Newton's first law. It's because of inertia that these objects are going to act that way. Okay, very cool, guys. Here's two more equations that you need to know. The coefficient of kinetic friction and the coefficient of static friction. These coefficients, once again, are just looking at the roughness or the smoothness, the slipperiness of a surface. If an object is in motion, then you're going to solve for mu. It's mu, like a cat, mu. Okay, so it's mu k, not nu, it's mu. Okay, so mu k equals F of k over F of n. Guys, check that out. That's 2D motion right there. Agreed? Because your F of k is going to be working left and right, F net x, and your F of n is working up and down, your F net y. So you're going to have to assess something that's 2D. All right, then over here, mu s is Fs max over F of n. So really, it's the same equation. You just have to assess, well, is it in motion, F of k over F of n, or is it at rest, Fs max over F of n? So if you have F of k over F of n, what are the units of F of k? The units for F of k are in newtons, right? What are the units for F of n? They're in newtons. So what are coefficients units going to be? Like what's mu k going to equal? What is mu s going to equal? Unitless. No units. Okay? There's going to be no units that are applied to this because they cancel out. So how do you solve for F of n when only knowing the mass of an object? Wow, this is great. You calculate weight. Weight of an object is F of g, whereas F of g is going to be your mass times the acceleration due to gravity. You need to be careful because if you're on an inclined plane, then you're really going to be solving for Fg of, well, you don't really know, so let's draw them both down. Fg of x or Fg of y, which this is going to create an hourglass triangle. So Fg of x is going to be sine theta times F of g, and Fg of y is going to be cosine theta times F of g. Okay, so that's how you're going to solve for f of n. There's more to it than that, but that's